and I would like to speak about some functional difference equations that arise in different applications of mathematical physics. And the plan of my talk is the following. I will consider some particular example of a problem. It's relatively simple but traditional in spectral theory, for example. Then I will show you how functional equations on a complex plane will arise. And then I will consider a more general class of such kind of equations and give some analysis of spectral and analysis of these equations, reducing them to some integral equations and studying integral operators, their spectral properties. Then we turn back to an example, and we shall consider some, not only spectrum, but also some properties of eigenfunctions. All this stuff will enable us to consider some methods and some ideas to study functional difference equations of different origin. So let's continue. First of all, let's consider such a simple model. We have a half plane. So we have y greater than 0 here, two-dimensional problem, and we have two lines, L1 and L2. This is the lines of support of delta function in the following Schrödinger operator. This is traditional Laplacian, and this is so-called delta function or singular potential. What does that mean? It should be appropriately defined, for example, by means of its quadratic form or its sesquilinear form. So gamma 1 and gamma 2 here are so-called Robin parameters. I will explain what does it mean in classical terms just below, but my idea is to study the following spectral equation. Here we have our operator properly defined on some space, and it's necessary to consider the spectral property of such a Schrödinger operator with singular potential that has its support on two lines, L1 and L2. So this simple model enables us to show how functional difference equations arise in this problem. And actually, this is semi-bounded operator, and we shall consider negative spectrum of this.
What does it mean, delta L1, L2?
Okay, this is formal expression. Informally, it can be defined by means of this sesquilinear form. We can close this form, and we can define the corresponding self-adjoint operator, this one. But below, I will study classical formulation of this problem, and your question can be answered, of course. So now I would like to turn to classical formulation. So we have half plane and three sectors, omega 1, omega 2, and omega 3. They are separated by two lines that are supports of delta function. So, sorry?
Do you denote those lines by L1 and L2?
Exactly so, exactly so. It can be shown here. Okay, so omega 1, omega 2, and omega 3 are three sectors, and we introduce, of course, polar coordinate there, and we have three Schrödinger's equation in each sector, and delta functional singularity on these two lines in classical terms are expressed by this boundary condition. We have Neumann condition on the boundary of the half plane, and we have these four conditions explaining or describing the corresponding delta function on these two lines. So we have continuity of the solution, and we have a jump of the normal derivative on these two lines. Here, gamma 1 and gamma 2, two Robin parameters. We assume that gamma 1 greater than gamma 2, but it doesn't matter, of course. So we expect some behavior at the origin where we have some singular point, geometrical singularity. For example, we can show that asymptotics near this point, something like that. And we also expect to find eigenfunctions. I explain you that we have a semi-bounded operator. We consider negative spectrum, and also there is an essential part of the spectrum, or essential spectrum, and below the essential spectrum we expect existence of eigenvalues of finite multiplicity, so we have discrete spectrum. And we expect that eigenfunctions exponentially vanish at infinity. So now I would like to turn to reduction of this relatively simple but important for us problem by means of incomplete separation of variables. Now I would like to turn to integral representation of the solution. This representation is of so-called Kontorovich-Lebedev type. Here we have representation in these three sectors, U1, U2, and U3. Here K sub nu is a modified Bessel or McDonald function, and it's important that it's exponentially vanishing when argument growth. So we have kappa is a square root of minus e, where e is a spectral parameter. So you see, we try to separate variables in these sectors. So phi and r, two polar coordinates, and there are known functions in this representation, h1, h tilde, h3. So actually, this is solution of the equations, and we should substitute it into the boundary conditions. And due to boundary continuity, we can exclude some of the unknowns in the integral of Kontorovich-Lebedev type. And we obtain the following system of functional equations, or we obtain this functional equation for two unknown functions. The other functions can be defined by, or can be specified by use of these two. And we have 2 by 2 vector H of these two unknowns. We also use some specific matrix. And we arrive to this functional difference equation. So actually, we arrive to known local equation. We have variable nu on the complex plane nu. We have shift to the right-hand side, shift to the left-hand side, and we have also meromorphic potential. So now, first of all, we need to solve our problem in the class of meromorphic functions. It's dictated by the problem at hand. So actually here, as I told you, we have such a functional equation. This is by definition meromorphic potential. Lambda is exactly the parameter which is connected with the spectral parameter. This is something like gamma 1 over square root of minus e, something like that. So if you have this at hand, then you can compute the value e, and vice versa. Gamma is the Robin parameter. So we have also such a diagonal matrix here, and we have a system of functional equations, or in other words, we have a functional equation number 7. And in our particular example, the matrix W, 2 by 2 matrix, is nothing more but some meromorphic matrix here. It's shown here, but in general, we can consider this kind of functional difference equations of the second order, implying that the potential W is some potential which belongs to a class of more general potential. But in our particular example, this potential has such a form. This is nothing more but combinations of some trigonometric function. This is meromorphic potential, of course. So, and the idea to solve this equation for the specific class of meromorphic potentials, we could see how this equation has arrived in our particular problem. But now I would like to consider more general class of meromorphic potentials. They should be odd. They should have asymptotics on the imaginary axis. This is unity matrix. And it's admitted some pole singularity at the origin at nu equal to 0. And it's also important, it's exactly the consequence from our example, that our meromorphic potential is positive on the positive part of the imaginary axis. I recall you that H is 2 vector, and our equation has such a form, where lambda plays the role of the spectral parameter, or it's better to say will be characteristic parameter. So now the idea how to determine, how to find solution of this homogeneous equation of the second order. This is no local equation on the complex plane nu. And we consider non-trivial solution of this equation in the class of functions that are described by these properties. You see, we consider even functions that are holomorphic in some strip of the width 2 plus 2 delta, and that are exponentially vanishing along the imaginary axis. So it's natural to formulate the spectral problem for this equation in the following form, we need to find some lambda for which this homogeneous equation has non-trivial solutions in the class of functions that has been described. So now the idea more or less simple. We expect to reduce our spectral problem for the functional difference equation to some well-known object like integral equation. Exactly the way for this is the use of this simple lemma, which can be proven by means of Fourier transform along the imaginary axis. If you have such a kind of functional difference equation with the known right-hand side, you can invert in a proper sense the difference operator in the left-hand side, and you will obtain the solution of this equation in such a form. This inevitably gives us possibility to get an integral equation instead of, or it's better to say, this is an integral representation of the unknown function h. If you have h on the imaginary axis, then you can continue from the imaginary axis by means of this integral representation from the imaginary axis to some strip that contains the imaginary axis. So we have plane nu, we have some vicinity of the imaginary axis 1 plus delta here, minus 1 minus delta. So if you have solution of your problem on the imaginary axis, then you, by means of this integral representation, you can get it on the whole strip. And then after having this solution on this strip by means of functional equation, you can continue your solution on the left-hand side and on the right-hand side by means of functional equation. So the problem is to determine it, is to find your solution on the imaginary axis. And now we almost have integral equation. You see lambda, this is spectral parameter, or better to say characteristic parameter. And after simple transforms, I would like to recall you that matrix W is positive matrix on the imaginary axis. So we put nu on the imaginary axis, you have such a simple substitution, and you will obtain immediately, instead of H you have Q vector, you obtain this integral equation. And it's a remarkable thing that this is integral equation on the imaginary positive part of the imaginary axis, because this function is an even function. Oh, sorry. Yeah, even function. So we need only to know it on the positive part of the imaginary axis, and you have an integral equation of such a form. This is a system, of course, of equation, because this is 2 vector. And the square root of the matrix on the positive part of the imaginary axis is also present here. A is a constant diagonal matrix. But now we are close to the main object to study for us. We obtain an integral equation. After additional transform, we reduce the semi-axis onto interval 0, 1, and you obtain an integral equation with such an operator, integral operator. Of course, here we have to study the properties of this operator. It's obviously symmetric. It can be shown that in L2 space on 0, 1, this operator is bounded operator, because the properties of these functions are well known, and we can show that this is bounded operator, and it's symmetric, so self-adjoint operator. It's nice property, excellent.
What is the integrating variable in this integral?
Y.
Why?
Y.
Why?
dy.
I see.
Yeah. Yeah. Mm-hmm.
And why can't you get the factor depending only of x outside the integral?
Oh, it's more convenient for me to have such a symmetric kernel. You see, yeah. We have symmetric kernel for this integral operator. We have bounded operator with symmetric kernel. So in L2, this is self-adjoint operators. Now we switch on all the analysis for self-adjoint operators now. You see, instead of parameter lambda, characteristic parameter, we shall use its inverse. It's a spectral parameter for operator K. And now I would like to use traditional, more or less traditional analysis. And spectral analysis of this integral operator is as follows. The operator K, we remember this is operator with this kernel shown here. It can be represented by its sum. This is singular part. It's a more regular part. V vanishes when x and y goes to 0. You see that when x and y is equal to 0, this is singular point of our operator. And we can represent this operator as a sum of 2 operators, M operator and V. So it's this operator is close relative of the well-known Karl-Liman operator. In the case of Karl-Liman operator, we have integration to infinity, but here I call this operator Möller operator. But it's remarkable thing that spectral properties of this operator are quite well known. This operator has its essential spectrum. So this is, by the way, this is a positive operator, and the operator K also positive operator. So for the operator M, we have essential spectrum on the interval mu plane. On the interval 0, 1, you have essential spectrum of this operator M. So the operator V here, this is a less singular summoned. So this is exactly in our assumption. This is assumption goes from our example, but in this situation, this kernel is such that the corresponding operator V is compact. So we have exactly a compact perturbation of the operator M. So due to Weyl theorem, the essential part of the spectrum, the essential spectrum preserved. So we have that the following lemma is valid. The essential spectrum of this operator K coincide with the segment 0, 1. So this is exactly the same. But we expect that on the right-hand side, from the end, from the edge of the essential part of the spectrum, there may exist some eigenvalues. So the discrete spectrum of the operator K may be non-empty. And exactly these points of the discrete spectrum will be responsible for the discrete spectrum of our initial problem in the angular domains for our singular potential, you remember. So the idea, are there any points of the discrete spectrum on the right-hand side from the essential spectrum? And now I would like to formulate a couple of sufficient conditions of existence of this discrete part of the spectrum of the operator K when this discrete part is non-empty set. And the first, the simplest condition of existence of discrete spectrum and at the same time of existence of the eigenvalues and eigenfunctions of our Schrödinger operator with singular potential can be formulated in the following form. So let's consider, existence of the discrete part of the spectrum on the right-hand side from the essential part, of course, is regulated by the quadratic form of this type. If you find some function u for which this inequality holds true, then you can expect existence non-trivial discrete spectrum. So we can introduce such a 2-by-2 matrix. So I would like to recall you that W exactly connected with the potential of our functional difference equation. We can compute such a value. We can compute the minimal eigenvalue of this matrix. This is symmetric matrix. And if this inequality holds true, then there is at least one point of the discrete spectrum on the right-hand side from the essential one. A bit more, okay, it's better to say an additional sufficient condition can be formulated in terms of spectral measure, or it's better to say singular sequence of the operator M, Möller operator. So we can construct a singular sequence at this point, at the end of the essential part of the spectrum. And then we can organize, this is such a function, and we can verify such an integral inequality. We have double integral. And here U is a Weyl sequence corresponding to the edge of this essential spectrum. And this is an alternative sufficient condition for existence of the corresponding discrete spectrum. Now, a few words about finiteness of the discrete part of the spectrum. It can be, of course, most maybe natural and well-known way to discuss finiteness of the discrete spectrum of this operator is based, okay, this finiteness is based on Biermann-Schwinger principle. And the theorem can be formulated as follows. So we can introduce operator Q multiplication by such a logarithm. We take its power alpha. We organize such a product of three operators. V is the operator that has been described here. So gamma is a constant. So this is Hilbert-Schmidt norm of this operator. So if these two norms are finite, it's exactly so when alpha greater than 3/2, then the number of eigenvalues that are located on the right-hand side from this point 1, this number is finite. Otherwise there can be infinite set of eigenvalues that, of course, can accumulate only at the end of the essential spectrum. So Biermann-Schwinger principle enables us to describe the finiteness or infiniteness of the discrete part of the spectrum. So, and now, of course, we can translate all this information onto this functional difference equation with the potential belonging to the class that has been described. So actually, we call the set of lambda 1 and so on, lambda n, in the case of finiteness of this discrete spectrum, we call these values, spectral values, or values of the discrete spectrum of this functional equation. And because I would like to recall you that this is mu plane, and lambda is equal to 1/mu. So the essential part of the spectrum for this equation coincides with this semi-infinite interval. I have at least 2-3 minutes, maybe, yeah? Right? Okay, and maybe a final results deals with the behavior. We turn back, we go back to our example, and it can be shown that an alternative representation for the solution of our initial problem with singular potential also can be given here. We have so-called Sommerfeld integral representation. It's a remarkable thing that the Kontorovich-Lebedev integral representation are not convenient to find the asymptotics for large distances from the origin of the eigenfunctions. But for this representation, it's much easier to find asymptotics. And the main result in our, okay, let's consider below, please. So we can find some alternative functional equation. Please, the next slide. We can find the far-field asymptotics, and the far-field asymptotics can be computed from this Sommerfeld integral representation. And the main, how to say, qualitative result is as follows. We can show that asymptotics depends on, the asymptotics is expressed by means of exponentially vanishing terms here. We have some vanishing exponents and some estimates of this kind when k is exactly square root of minus e. This is e is the spectral parameter. And tau m corresponds to a particular eigenvalue that we have just considered. And the physical or asymptotic effects is as follows. There are some directions in these three sectors where the rate of decreasing changes. So, and this change is expressed by means of, please, the next slide. So we have at least some directions along which the rate of decreasing of the eigenfunctions varies. So this means that in these directions there is some special function in order to describe asymptotics must be used. This function is exactly a Fresnel type or error function. So it's shown in this case, the uniform asymptotics for the eigenfunction includes this special function. This is nothing more, but this is error type special function. So the conclusion is that the rate of decreasing of the eigenfunction changes smoothly in some direction. So this is maybe final, but to my mind, interesting observation dealing with this problem. Thank you very much.